Okay, in the last video we discussed the Bernoulli principle and that equal transit argument for lift. And we did say that if you wanted to use the Bernoulli principle, you could just say in a wing that produces lift, airflow over the top is faster than airflow along the bottom of the wing, and therefore you've got higher static pressure on the bottom than on the top, because faster air has lower static pressure. So we have faster air on top of the wing, okay? If you have faster air flowing over the top than along the bottom, it's going to create lift, okay? So that's a nice explanation, but like I said, it has its problems, okay? It doesn't really explain why the airflow over the top is faster. It doesn't explain how a wing can fly upside down, all those sorts of things, okay? But it is an accepted explanation for your HSC. And quite a few people, if you ask them how a wing produces flight, that's what they'll say. But anyway, let's do the turning force argument. Now, the turning force argument relies on the fact that, and this is probably a truer explanation of how a wing produces lift. If you were to put your hand out of a car window as the car was speeding along, and I would not suggest you do this because it's very dangerous, but if you were able to do it on in a place where it was completely safe, and I have done it in places that are safe, when you tilt your hand back like that, if the wind's coming, hitting your hand in this direction, if you tilt your hand like this, it goes up. If you tilt your hand like that, it goes down. Tilt your hand like that, it goes up. Tilt your hand like, and it kind of makes sense because when you create this angle, that's called an angle of attack, okay, on the actual wing. When the wind hits the wing, it's going to tend to push it up, okay? So intuitively, it kind of makes sense. So that's called angle of attack. And that's why a plane can fly upside down, because when you flip the plane upside down, they'll drop the tail to create the correct angle of attack to keep the plane in the air, okay? So angle of attack is very important in flight situations. So your wing, if you want to talk about how it produces lift, and we will just draw the same shape as we did for the Bernoulli principle, but it could be a flat surface, it wouldn't really matter. Actually, we will draw a flat surface because this is kind of the explanation that sort of meets that idea. So if we draw our wing, and you can see there that it has an angle of attack on it. So we can see here from the horizontal, we have that angle, okay? That's going to be, I'll just say with a big A there, subscript A for angle of attack, okay? So the wind, our airflow, as the aircraft is moving forward, is coming in this direction. Okay, so you might notice something. When it hits this part of the wing, what's it going to do? It has to turn. It has no choice. It can't go through the wing, so it's going to be deflected down. Now, this is where our Newton's laws come in, okay? In particular, Newton's third law. So I'm hoping that you remember the three laws. There's the first law is the law of inertia, essentially. Okay, so an object remains at rest or continues to move at a constant velocity in a straight line unless acted upon by an unbalanced force. So what that's telling you basically is this object will continue to move in a constant velocity or stand still until something happens to it, okay? Now, Newton's second law is force equals mass times acceleration. That's how it's explained with a formula. And the final one is the one that we're going to be talking about here, is for every force there is a reaction, okay? So that's kind of the idea of, if I'm pushing on the board and I'm not going anywhere, that's because the board is pushing back in the opposite direction, okay? Every force has an opposite reaction, okay? So when this wind, or this airflow, hits the wing, it has to turn. Now, an airflow, although it's not a solid object, So it's always a lot more complex. Fluid dynamics is a lot more complex than just, you know, the physics of solid objects, okay? There's more to it. But we do know that that air mass that's flowing, or that air has a mass, okay? So it's still going to be obeying Newton's laws on some level. So when the airflow hits the wing, the airflow has to turn. The only thing that's going to cause it to turn, because remember we said it continues at a constant speed unless acted upon by an unbalanced force, okay? So there's a force that's applying itself to that airflow. Which way is the airflow going? It's going down. Now let's not talk about directions and the ins and outs of the physics here, but we do know that there's a force that is making that airflow turn, and it's going down. So if we've got a force turning the airflow, something has to react to that force because of Newton's third law, and that is going to be a force acting up. And we call that force that's acting up, okay, so this is our direction of flight, arrow. Direction of flight. This arrow here is it's called lift, okay, so that's the lift force. So this is, this whole theory of lift, okay, is called turning force on airflow. And you might think, well, what's wrong with that explanation? We've explained it, and it's great. The only problem with that explanation is that the air coming in this direction is not impeding on the top here, so you would think that it would just keep going straight. But it doesn't do that. We know in wind tunnel tests, and there'll be a video under here showing you this, that the airflow on top also wants to follow what's happening on the bottom. Now, you will see videos that try to explain this by saying it's the Coanda effect, okay? You'll see videos that are online saying it's all due to the Coanda effect. You'll even see aeronautical engineers saying this, but there's quite a few PhD physicists who say that the Coanda effect is not the cause. The Coanda effect is if I had like a round bottle, like the end of this pen, and I poured some water on it, the water would follow the outside of the tube and then fly off. So a stream of water tends to follow the object that it's flowing over. And I can show you that. They sometimes demonstrate this with a sheet of paper. And what they do is they hold the sheet of paper so it's flowing down, and when you blow over the surface of it, the paper lifts up like. Can you see that paper lifting? Even though the wind flow is just going across the top of it, it's lifting, okay? So the airflow over the top is actually causing it to lift. Now, they're saying that that's the Coanda effect. The Coanda effect is a stream of air over a stationary surface with stationary air on its surface. This is not likened to that situation. So they say it's like that, a lot of the people that explain it that way, but there's plenty of people that say, no, it is not the Coanda effect. You can't use the Coanda effect to explain this. Other people say, and this argument's kind of convincing, is that if the air was to flow straight across, okay, you are going to create a vacuum, okay, because the further apart these lines are, the lower the pressure, okay. Think of meteorological chart with isometric lines on it, okay. So if the lines are not following here, you'll get a vacuum here, and that sucks that airflow down onto the wing surface, okay. That argument has its merits too, but you'll have this idea that if that was the case, well, why at certain angles of attack does it suddenly decide it's not going to do that anymore, etc., etc. So it's a very complex situation. It's probably best to say that the turning force of an airflow and Bernoulli principle are all beneficial in explaining lift, okay? Bernoulli principle explains it well because you've got a faster flow on the top than the bottom, which can be verified physically in a wind tunnel. And the turning force because we know that with the angle of attack, you have a deflection of airflow, okay? And deflection of airflow means there's a force acting to cause that deflection, and lift is the opposite force in reaction to that turning force of the airflow, okay? Like I said, where it gets complex is explaining what's happening on the top surface of this in that situation. But suffice to say, if you want to predict what's going to happen and really understand it, we have all the tools we need in a mathematical and physical sense. But unfortunately, if you want a layman's explanation of lift, those two examples, the Bernoulli principle and the turning force on airflow, are the two probably best explanations. You could almost say that once this angle of attack happens, you get a lower pressure system on the top as a result, and you've got higher pressure then at the bottom, and it's almost like Bernoulli and Newton are working in concert to make it all happen. Okay, but I would suggest if they ask for a theory of lift, you could mention the Bernoulli principle or turning force of an airflow, or you could actually talk about both if you feel really confident about it. Okay, so turning force of an airflow or Bernoulli principle are the two ways for your HSC you're going to need to discuss how a wing produces lift. Okay, so hopefully that helps. I'll try and find some succinct explanations that you might be able to write as a response in the examination. You could even maybe, if you've got time, put them both in to indicate the depth of your knowledge of how a wing produces lift. Hope that's helpful, and I'll see you in the next video.